All right. Good morning, folks. Today we're going to be studying a little bit something about level process control. I have it set up here as shown. There's going to be one tank at a certain elevation that will drain through an orifice to a secondary tank, and from this tank, uh, we'll have a pump that will push back the water to the first tank. So yes, this is not a perpetual machine, not at all. I mean, you need to put power here just to get the water back to the first tank. So the idea is about control, process control. So we want to be sure that we change the flow on this pump so that we can control the elevation of the water in the primary tank as shown here. So the idea will be something, let's see, my setup is something like this. There's a tank here with an orifice, as you can see, water coming to the secondary tank, and there's going to be a pump here that will push the water into the first tank. The idea is that if I am able to match this flow rate with the one getting into the vessel, then the level will stay at a steady state value, or at a set point, if you want to say it like that, at a given set point. So you change the set point, and either the flow rate from the pump from here to here, pushing the water to the top, will change accordingly. In the primary vessel, I already have an ultrasound sensor that will detect the water elevation. This needs to be calibrated with the vessel, and all that has been done. We have good data when the tank, when the level goes down, we can monitor that with the sensor and the Arduino connected to an Arduino that is in this box, and we can collect all that data and transfer that to Excel and do all the fancy analysis, all the math analysis that is required. But in the meantime, we are missing this part of transferring the water back automatically at a certain rate to ensure that we can maintain the level within this primary vessel. And this video in particular will be about this last part, how to control the flow rate of a pump. And for that, we're going to be use pulse width modulation. We're going to use an Arduino to do those pulses. And here is the pump. This is a 12-volt pump, very cheap. It's about $5. And we will connect it as this setup, and hopefully we will get, we will be able to control the flow rate of this pump without damaging it, causing any trouble. Because it's not good to do on-off on this type of pump because it's going to damage the motor. Well, with that said, let's get started. All right, here we are. We're going to do our simulation in Proteous about our pulse width modulation. So let's start with my launching here Proteous and new project, and how about a pulse width modulation DC motor, and that would be rep 1. Next. We're done. Finish. Here we are. We're gonna do our simulation using an Arduino. Let's see. So let's start by picking one Arduino from my library. I think I have plenty of those here. Mega. The Arduino Mini, the Nano, the Mini. I'm going to use this one, and the reason is in most cases I always use this one. I like this one. If you check all my simulation before, all the work that I have done using Arduino simulation in Proteus, I always use this one. Somehow I try to use this one for fast pulse width modulation, and it failed. Pin 5 and 6 on this library is not working right, so I'm not sure what it is. whether I have the latest version of it. I haven't checked that out. So I'm gonna try this one and see what happened. I had never used this, but it seems like it might work based on what I have seen on the internet. So let's use that one and let's say okay, and let's put that guy right here. So that's it. Now let's add, since I'm using, I want to see the frequency of those pulses. So let's add a counter. Let's put that somewhere here. And let's see. So it's gonna be, whether it's gonna be 6 or it's gonna be 5. Let's pick 6. Gonna pick 6. I will do. Now change the timer so that we can read frequency. That will do. Now let's to check the width of the pulses. Now let's use an oscilloscope. Let's put that somewhere here. That will do. And now let's connect that from here to here. So I have the oscilloscope to check the pulses, and I also have these to check the frequency of my system. All right, that will do. Something about the pins in the Arduino that you always have to be. So before we go any further, let's check what is fast and what is slow from the point of view of pulses. If you go, for example, to your Arduino reference, let's go here for a second. I'm right there for the analog right, which is the one that I'm going to be using on the code. The Uno, these are the pins that you can do pulse width modulation, 3, 5, 6, 9, 10, and 11, but they are mostly 490, except for pin 5 and pin 6 that they are about 980. So I'm going to be using 6, which is 980. So that's what I was saying. So it's going to be like we call it fast pulse width modulation. All right. So let's go back to my Proteous here, and we got that clear. Let's see what else should I add just to test this. I can quickly do. I'm checking. I can add, for example, let's go here. Here, and let's add potentiometer. Let's add one that is active, and let's put that somewhere. I can put it here. Oops, that will do. So the idea is that I will use my code so that you can adjust the width of the pulses based on the value that you are reading here on your analog. So I can put these. Let's add a battery here. Let's add a battery device. Can use any. I will use a multi-cell. Put this somewhere here. And now, so let's add a ground. Oops. There we go. That's correct. Now I have, let's put a ground somewhere. Put it here. That will do. So the idea is this. Let's bring this down here, and now let's bring this one as well down here. And so this is the positive one. We'll go right here, and let's ensure that I have the right voltage. That's 9 volts. Should be 5 volts. That's going to the Arduino, and from this is the one that I need to connect to. Oops, let's do this right. Let's connect that to A0. That will do. So if I adjust this, then you will be reading that through your analog 0, and adjusting your code for your analog right that you're going to be putting right at port 6 of the fast pulse width modulation. I think that we have everything that we need so far. Let's see. Let me take a deep look. The only thing that I need is to add the code to this, and we will be in business. So let's check the code very quickly. Analog code for a pump. I've just put this together. Integer let pin equals 6. So it said let because this is a code that is, I mean, it's in the internet. I can pick, you can put a pump if you want to change it. I leave it like that. It is from the Arduino reference pages. And so the idea is this. I'm going to connect the analog pin, pin 0, A0. And then pin mode. It's going to be an output. So pin 6 is an output. Serial begins, so I can write few things to the monitor, so I can see, so I can watch the value as I change it from 0 to 255. So I read the value and then write it here. So this, remember that the analog write is from 0 to 255. So the analog read here is from 0 to 1023. So definitely have to be divided by 4 so it get adjusted as shown here. So this value, again, you write that into your pulse width modulation, and then you do a write to this. Oops, so that means that I'm missing one particular item. Let me add that up. I'm missing the serial monitor. So let's go back here and let's pick a virtual terminal. So let's put the virtual terminal somewhere here. And so let's see. So this is the RX. The RX need to go to the TX, and then the TX from here need to go to the RX from here. So I got the terminal. Let's go back to the code. I got the serial printer already there. I got a delay. This is the interesting part of using this highly portable code. I'm not using the register for the pulse width modulation. You can use registers definitely, and you can do a lot of more fancy stuff with the register. However, I'm testing just the analog write and see how good I can adjust the voltage, well, of the RPM required at my pump. That's basically the idea. For that, I need to use pulse width modulation because I'm gonna be using a MOSFET, and you will see that in a second. The whole thing put together. But so far, I'm only testing the Arduino part just to see how well it works. Just the Arduino. I want to see that I can adjust the pulses. If I can adjust the pulses right, we are in business. That's basically it. For the second part, which is adding the MOSFET and everything else, and the motor, the DC motor, and all the parts that I need to have the MOSFET in place. So look good. Let's generate this. Generating the code. And have you used Arduino before with Proteous, you need to look for a particular file, which is actually the hex file here. Let's get this and let's move this. I need to look for a hex file, which is the executable file that I need to install in Proteous. I'm copying this up to here. Copy that, control copy. Now go to your Arduino, to Arduino in Proteous, and here paste that there, and we are okay. That's it. One extra thing that I might be in trouble with is the fact that I don't see any ground pin on this Arduino. This is the first time that I use it, and I don't see anywhere that it says GND or something like that, meaning that somehow it is a virtual ground, or it's pulling the ground from whatever you have. You said it is ground. You don't need to add a 5-volt either to power it up. The other Arduino, just for the sake of the argument, let's bring one down here. Let me bring one very quickly, just so that you compare what I'm saying. Arduino, and this is the one that I pretty much always use, this one here. And if you take a look to that one, And actually, let's bring it. Okay, and I'm gonna bring that somewhere here just for a comparison. Let's say here. That's good. All right. You can see that this one has a ground and a 5 volt that you can input. I mean, to make it work, you input 5 volt here, and this is the ground. So the Arduino, you are identifying a ground. There's a ground. On this one, I don't see it. So it does not mean that it will not work. It might seem like the library here pick the ground from whatever ground you have already in your system. So for me, that's good enough. If it works, it works. It's just that this one requires a little bit more connection to be sure that it works as you want. The only problem that I found is when I use this guy, fast pin 5 and 6 did not work. I mean, it did not work with that piece of code, or with any code, either if I'm trying to use the register directly or using the analog write. Nope, it did not work at all. So that's why for this particular project I have to discard the use of the blue Arduino. All right, so let's eliminate this one from my escape. Delete. There we go. Well, as I explained that to you guys, so let's go back here for 1 second. Let's centralize this. We are ready to rumble. The only thing that I need is to launch this, and let's see what happens. All right, let's move this to the side. I see good indication that I have. Oh, for a second I got scared. I didn't saw any frequency here. It was measuring the frequency. So it says something like, hard to read, but I think it's a 913. Maybe there we go. That looks better. 976, which makes a lot of sense, because if I go back to the reference, it says fast 5 and 6 are 980 hertz, and right now I'm about 976. So I'm right on the money. Looks good. Looks very good. How about the pulses? Looks like, I would say, 50%. That makes a lot of sense. That's the 128 that you see here. I'm using 1K here. Maybe I should make it this larger, like about 10K. Maybe it still work. Let's see. Let's do, if I go up, the off section should get smaller and smaller. Well, we'll see now. Let's see. Yeah, it's staying on all the time. This should go to, if I go to about 200, it should, yeah, perfect. I still see the 976 pulses getting bigger and bigger. This will work for my motor, definitely. It look good. And the nice things that I like this is I'm using analog write. Very simple stuff. And if I'm doing like process control within the loop, I can build very, put a lot of code in there. But the pulses that are going to the DC motor controlling the, let's say, the pump, the water pump, will not be affected by the many delays that I put in my Arduino code. Like, for example, let's check this. Maybe you didn't realize, but there's a big delay right there, and it's not affecting this delay here about 100. Maybe you think that that's small. Well, it is enough that will, if you are trying to do pulse width modulation within the loop, not within the register, within the loop, this will destroy your pulse width modulation. It will not work at all. Believe me, it will not work. So that has to be done through the register, either using this instruction, the analog write, or doing directly to the register, which is kind of a pain going through those registers. When you set it up, you don't want to change it at all. So, but I like this. I mean, from the portability point of view, this is great. Now, going back to the same issue, I can change this. Let's say I've increased this to, actually, let's go back here for 1 second. If you don't believe me, stop this code and go back here to Arduino code, and let's put here 500. That's, oops, sorry for that. 500, that's half of a second. That's a lot, a heck of a lot of a delay. Because let's say that you want to read, you want to do an analog read and get the average of that analog read, and in that case, you know, you have a big delay within the loop, but that will not affect the frequency of your pulses, which is great. So I put 500. Let's generate this. The nice thing is that since I already have connected my IDE with the Proteous, if I make changes here, I don't have to copy the hex file. It's already there and it's already alive. So basically, when I do here my run, it will pick the new build code. So run it, and you will see this number changing every half a second, basically based on this number here. 215 right now, which I leave it right there at 215. You can see that the pulses drop a little bit. Oh, there we go. Now, I thought that it was forever, but now coming back. 975, 975, 9777. Great. Let's see if I go. You see, the time here is pretty small. The power off, the power on is, you know, compare, it's pretty much on all the time. So let's go up a little bit more. Now I'm getting 220, 222, a little bit higher, 227. 230, 233. Yeah, it's looking good. I mean, pretty much there. I mean, if you have a MOSFET that is using these pulses, pretty much will be on. You know, will be fire. So will be pretty much in short circuit, and so current will go through it very easily. Let's see if we go here, drop it to the pretty much the bottom. Let's see. Well, you see how we quickly adjust I'm still pretty much at the same frequency, which is called a fast pulse width modulation, but it's pretty much off. Well, this is working like a charm. I have nothing, you know, to say against it. It's perfect. It's doing the job the way was meant to be done. The Arduino is doing, I mean, a lot better than the blue that I started to use before. Was having some hard time with the blue one, and I said there must be something weird within that internal library. I don't know how old that blue Arduino was. Maybe the new version have improved with this issue, but the fast pulses on it are not working. So I think that this is more than enough. Let's stop here. I stop. Now, this is the idea. The idea is to control a motor, a DC motor. So I need few items here to do that. So let me start that right now. I can either pause here, start a new video. So I'm not sure. I will do one in one shot. So okay. So let me add few here. Let me add a MOSFET. Let's see if I can pick a right MOSFET here. I would say is wow, it's a huge leaf of MOSFET. Yeah, it's gonna be 540 maybe. I can 540. I'm looking for a MOSFET 540 maybe. I need NS. NS. There we go. Here we go. Let's see what we have here. It's a MOSFET. uh, 540. About this one, this is the 33 3.8 single MOSFET. I would pick this one. How about this one? Is any difference on it? 33 amp, 36 amp. Huge amount of amp for what? All right, so let's pick this one, the IRL 540 NS. So okay, let's put that somewhere here. All right, so now I need a motor. Let's pick a motor, DC motor, DC motor, DC motor, animated with inertia and loading. Wow, this sounds like everything that I would like to have. Position encoder. Nope. I will use this. Seems to me okay for simulating a pump, a water pump. Always a water pump will start with heavy amount of loading. I mean, moving that impeller and that full of water will always be a high loading. So let's pick that one. And a motor. So let's see. Let's add that here somewhere. Okay, that will do. Let me double check on this one. So it's a 12-volt motor. Good. Coil resistance 12 ohms. Load max torque. Let's move it to 80. Kind of higher. Let's see if it's okay. Now, the idea is let's add a DC ammeter. Let's put that DC ammeter somewhere here. Actually, okay. Let's see. That will do from here. It will look kind of weird. Oops. Okay, but doesn't matter. From here to here. Because the positive will go right through here. And I wanted the motor spin this way, maybe. I don't know. Let's see. That will do. Now let's pick a battery, which I think that I already have a battery. Put a battery somewhere here. And that will be from here to there. And this will go to, oops, sorry. And this will go for my negative. All right, that will do. And this need to go here. So let's see. This one need to go to here, but here's the trick. I'm gonna, instead of having this working on an on-off basis, which I don't like, because that will impose heavy loading on the motor as well. I might quickly destroy it. I will use a filter. So let me add a few things here to make life easier. Let's add a DC voltmeter. And this voltmeter is only to check the voltage at the base of the MOSFET. And now let's add, I need to add, I don't see it here. Let's add a resistor. Resistor. A resistor. It's kind of a slow. There we go. Resistor generic. That will do. Okay, so let's put that one here. And now that's a 10K. Good. That's to ensure the in my particular case, I want to ensure, always creating problem, rotate clockwise. I want to ensure that when this is off, the this guy is switched off. So I'm putting that 10K right there. So let's see. That will do. Now let's move this a little bit closer. Yeah. Now I need a filter, so I will add electro capacitor. Generic. How about this one or this one? Actually, this one. Okay, put that there, and let's rotate that guy. And so that would be here, and connect this one down here. And now let's change the value of this guy. It's gonna be 10 microfarad. Whoops, I think that I put another number there. Yeah, it's gonna be 10. Alright, so I got the filter on. Look like I got everything that I need. The voltage here is not right. Voltage here should be 12 volt, and that will do. I think that I have everything. I can put a diode across the motor, but I'm not at this point. I mean, it would not matter at this point for the simulation. So I got the motor, I got the voltage going through, so I can measure the amps going through the motor. I set the motor with the proper amount of loading, 80. Okay, you don't want to put that at 100%. Obviously, it would not spin at all, even at maximum current. So this is the MOSFET will fire up according to this filter here, and a voltage will be set pretty much at the base based on the frequency and the width of the pulses. So in this part here, it's like before, I would be adjusting how the thickness of that of the pulses. Well, looks good. This is it. Nothing else on the simulation. Not even at the code. The code stay the same. I don't have nothing to change here. In fact, this delay might reduce a little bit, just because I want to be able to change those numbers quickly. So 100, maybe that's good enough. I want to generate with that. And now let's go back to my simulation, and we are ready to rumble. Let's do that. Let's see what happened. Run. If I screwed up, I think that I did. I see a weird thing here. Let's see. I can see very weird pulses. Let's go back. Oops, sorry for that. I see. No wonder. I said I couldn't. It's just that there's now a limiting resistor right here. I said something was weird. Check this out. I'm missing a resistor here. That's how important that resistor is there, and you will see that in a second. Let me stop here somewhere, and let me delete one line here, and you will see the big difference when I add that resistor. I said there's something weird, and here's the weird part. Put that there, and now let's connect this. Well, that's ugly. Connected there, and from here to here, and let's adjust that one to 1K. Now we're talking 1K. All right. So let's see if it works now. Run. Oh yeah, much better like before. I haven't. Oh, there we go. 913. It's still measuring, so you have to adjust a little bit because I can see that they are perfect right here. They are doing great. Yeah. Now we're talking 976. Perfect, right at the money. Now, see the voltage at the base of the MOSFET. That's the important part here. Basically, nothing is happening at the MOSFET because it's this. You check the description for this guy, 540. It's about 2.40 to be fired up. Somehow, if you get to 2.5, 2.6, it pretty much is already on. So I mean, it will be like a short circuit going through it. As you can see right now, there's no current at all going through the motor. The motor is now spinning. So I have to do, like for example, some adjustment here. If I go up, before I doing that, let me increase this so you can see better those width. Let's see. I would say that would be okay. It's pretty much off. 30, that's off. So let's go quickly here. It's going up. See how thick it's getting, the pulse. Now, but I don't see anything here happening. But yes, the voltage is going up, which is good. It's good. That means that somehow I might get to the point of firing the MOSFET. The pulse getting bigger. I mean the modulation. You see, and but the voltage is not yet at the firing level that is required. So let's keep going here. I'm about 100. Nope, in 100 nothing happened. I don't see any action. But the voltage is up 185. Still require a little bit more to go up at 100. I still need to go. I mean, the maximum will be 255. Whoops, I'm in the wrong place. Let's put it. There we go. So I'm 112, 117. 227. I'm about to 125. Seems like where things might start because the voltage is 220 something, getting very close to where the MOSFET will start firing. 130. How about there? Yeah, 130. Yep, about 230, and I can see some amp trying to go through. I mean, it's not a big deal because the motor is hardly spinning at all, as you can see. But again, at 130 is where you start to cook, you know, whatever you want to control. Like you want to control this DC motor, this guy will start to fire when the voltage is about. I mean, this guy will start to fire when the voltage is about 220 some, 230. And now, if I go here one by one, you will start to see the motor spinning faster, meaning more current going through. 133. I can see a number that looks like 90 or something. So there's an intention of the motor start to spin, because I can see a number here about 3 RPMs or so. So 133, you start to have some minimal action. So going up a little bit more, 135. Yeah, 135 you start to see some 100, about 100 milliamps or so going through, and you can see the motor spinning. Remember, this motor has a loading of about 80%, so it's like I'm trying to simulate a water pump. Okay, so and the voltage is here. It's about 2.4 volt, and I saw a number here flashing for some time of 140. Maybe if I want to create a graph of the voltage, it would be great to take a look at it, but not now. It's more than enough. At this point, I know that this is really working. So a very simple code and very simple simulation is doing the job. So let's go in. There we go, 140. Well, at 140 now you're talking from 130 to 140. You're talking now. You have about point 0.8 amps, and the motor starts to spin faster. Remember, it has inertia. You need to battle that inertia, and this simulation will take a while. I mean, it's going. I mean, I'm about CPU loading 58%, meaning I'm not simulating in real time. It's okay, but in a couple of seconds, you see, now it starts spinning faster. So it's gonna take a few seconds here and there just to get that motor to fast speed. I don't know, like 200 RPM. It will take a while. So that's part of the control process that you need to ensure that you understand that when you put your parameters for the constant required for your control output. You have to build the fact that this has some kind of slow response. Now it's going to 142, spinning faster. The amps stay there. If I increase this more, 146, that's basically it, 83, almost 1 amp. Remember, the coil has a set 12 ohms coil plus whatever resistance you have here. That makes sense for this value. Looks like that's it. 81. Maybe if I get this to the maximum, let's jump here. You see, the amp still the same place, never change. So that meaning that the MOSFET is well fired. For this MOSFET, the nice thing about it is that it can be fired within the Arduino voltage. So within the 5 volts, it's pretty much fire. If you want, it might get hot a little bit because, I mean, 1 amp going through, maybe not. What I'm saying, maybe not 1 amp, maybe 2 or 3 amp might get hot because there's some resistance value when you fire it at this voltage. If you don't want that resistance value to be lower, you have to fire at a higher voltage. This guy typically requires like 10 volts, but at 5 volts get the job done for the Arduino, and that's why I like it about it. You can see I'm basically 243. I can go a little bit higher than that, but the voltage, I mean the amps at the motor are not changing. I mean I can go, let's see, the maximum will be 255. I don't see any change at all. See, just to make the pulses 977. It's hard, in fact it's hard for whatever to measure those pulses because now start to mess around, I think, with the pulses going. There's no pulses going down, so everything like it's not pulsing right. You see, it went off. No big deal. Yeah, now I have truly a 5 volt there, and I mean, that's it. That's the way it is. If I go the other way around, down here, pulses show up back again, but they're pretty much off. And now the voltage at the base of the MOSFET is pretty much off. So there's no current going through. You can still see the motor spinning. It's just the inertia part, which I like it about it because it's trying to simulate the most close things that I can have, like for a pump, a water pump. Well, this is basically it. I mean, it works like a charm. The next thing I will do is construct this, you know, do the whole thing. And before doing that, remember, this is part of a process control project in where I want to control the level in a tank. And so this part here is for the motor part. Okay, this will control the water pump. This part here, which seems I'm using it only to provide the proper pulses or the pulses width to the Arduino. This will come from the fact that I will be reading the level at the bezel. So if you read the level at the bezel, obviously I will not use something like this. I'm planning to use something like let me stop this simulation here for 1 second. I'm planning to use, let's see, I think that I saw it here, Arduino, this guy. I hope it works, that guy. I haven't tested. So that will be a piece of a unit, that I will connect to my Arduino. So this guy will be reading the level of my bezel based on a set point that I established. Actually, I can certainly use these as my set point from my bezel, and whatever you adjust on this is the PV. This is the actual value, the level that you have, and this is what the set point that you want to have. So within the code and the proper constant for your controller output, that will be required to adjust the pulses width and so forth. So you will have then you pump, adding water to that vessel as required, because this vessel, the vessel that I will be controlling the level, has the pump will be used for getting water in, but it has an orifice, and the orifice will constantly spill water out. So to maintain a level, you definitely want to have a flow of water going into it. So that will be the idea. The idea is to have this to measure the level, perhaps use this to have the proper set point that I want, and to use pulse with modulation to control the inlet water flow. That's it. As I always said, be safe, whatever be your final destination. Thank you and have a nice and great day. Bye.